Last time we defined an algebra of sets on a set X to be a subset of the power set, so a collection of subsets of X, which contains the empty set and is closed under finite union and is closed under complement, where complement means complement in X. So for example, the complement of the empty set would be X, so it also has to contain X. It also turns out that when you do this, they're automatically closed under finite intersection, because when you take complements of unions, you get intersections, and it's closed under complements. Now, we extended this definition and defined sigma algebra on X. Then we don't have to say of sets usually. We just say sigma algebra on X. And all we need to change for that is it's closed under countable union, so more than just finite. And again, since it's also closed under complements, it's closed under countable intersection. We also defined the notion of a sigma algebra generated by a set. So let X be any old set, and let F be any collection of subsets of X, so subset of the power set of X. Then F might not be a sigma algebra, it might not be an algebra of sets on X, but we can talk about the sigma algebra it generates, the sigma algebra on X that it generates. And that would be something which we have this notation for, sigma of F. That's the sigma algebra generated by F. And we can take it to be, we can define it like this. It's the intersection of all the sigma algebras on X that contain F. And last time the way I wrote this is I wrote big intersection symbol, and then I wrote just A with no curly braces here. And then all the text that you see here was written in small print underneath the intersection symbol. That's the same exact thing. Those are just two different notations for the same thing. In general, the big intersection symbol and the big union symbol can be applied to sets, even without any indexing. So what I'm referring to is this idea that you're used to using big union and big intersection on an indexed collection, so maybe A, alpha, alpha in J, or something like that. But when you're doing that, you're actually just using a special version of this, which is part of a more general notation, which is this: the union of a set, the intersection of a set. So the union of a set is the collection of things that are in all the elements of the set. So you think of this set as a set of sets, and the union is, the intersection is the collection of things that are in all of the elements of the set. And the union is the set of things that are in some element. So to be in here, you have to be in some element. So I'm talking about this because I've been getting some homework-related questions about working with the union and intersection. And when you do work with it, remember that they have these formal, precise definitions. So if you're ever wondering, is this true from set theory, is that true from set theory, well, you can prove it yourself, because here are the definitions from set theory. All right, so this is an equivalent way to write what I was writing before. And it's nice because I don't have to write all this stuff in small print. Now we can also define, okay, so we came up with two ways to describe what is the sigma algebra on X generated by F. On the one hand, we said it's the intersection of all the sigma algebras on X that contain F. That's what this notation says. On the other hand, we said it's the unique smallest sigma algebra on X that contains F. We proved that those are the same thing. Now, one thing that is in your reading but that I did not define in the lecture is there's also the idea of an algebra of sets on X generated by F, without the word sigma. There's no official notation for that I found, but we can just temporarily use this notation just for this discussion. Instead of sigma F, let's call it alg of F. And same idea. You can express it as the intersection of all algebras of sets on X that contain F, or you can describe it as the unique algebra of sets on X that the unique smallest algebra of sets on X that contains F. and those can be proven to be equivalent, just like last time, using the principle that if you intersect two algebras of sets, then you get another algebra of sets. Or if you intersect any number of algebras of sets, you get an algebra of sets. Okay, and the question we left with last time is, can we describe, we actually left the question about this, can we describe this constructively? And I want to bring this up because we actually can describe this one constructively, and we're going to have some trouble with this one. To understand what is the difficulty, why this is so hard, it's helpful to look at how things go well with this one and then what aspect breaks for this.